And I'm going to move that down to the board. Yes. Okay, so you have some, those of you that remember using your TIs in earlier math classes, you can futz with this, which is kind of cool. So this is the default. And very often, all we do is we throw the histogram up to get an idea of the shape of the data. So how would you describe that shape? If you had to pick a few words to describe that data's shape.
Skewed.
A little bit skewed? How come?
Because it's like dramatic. Yeah.
I like that because I'm seeing a little bit. We got kind of like a heavy side on this side, but it's not excessive. It's just a little bit on that side. And the problem with real data, a characteristic of real data is nothing is ever perfectly symmetrical. Jordan's like, how dare you, sir? Nothing's ever perfectly symmetrical. I mean, even the human body, looking at data, the human body essentially is longitudinally symmetric. But look at yourself in a mirror sometimes. I mean, it's amazing how there's little tiny variances. But none of us would call our bodies skewed because of little tiny variances. So, okay, Jordan, maybe you would. This guy, I love this guy. So what I want you to do is, I want to explore. Remember, this only looks the way it did is because we use the TI zoom stat default. And by default, that places 7 regions to place the data into. So I want to show you how to finagle with that, okay? If you press the window button, which is this guy right here, you can. There's 2 things that I like to kind of change in this window. Actually, it's more than 2. I like to futz with all the X's usually. So let me tell you first of all what zoom stat or zoom data in the 89 is doing. It's essentially making the window wide enough and tall enough to put your data into it. Notice the min is -58, the max is 34. That traps the data. Your lowest data point was -58. Your highest was 21, I believe, wasn't it? So I'm kind of out to lunch as to why I put 34, but whatever, it did. So I'm going to change those a little bit. I'm going to change xmin to -60. I'm not going to use that. I'm going to use negative. I'm going to do this first. Sorry, guys. -60. X max, our biggest data point was 21, right? So I'm going to make it 30, not 34. Okay. Slide that down so you can see it. And as far as that X scale, the X scale tells you how wide the bars are. So right now, each bar is 13 1/6 pounds wide. That's a strange number to keep in your head. I'm going to pick 10, because 10 is actually a logical number that we can actually kind of see, if you will. So I'm going to make it 10 wide. Now the Y mins and maxes, I would leave them alone until you press the graph button to see. So I'm going to go ahead and press graph. And there's a new look at our data. There's a new look. Now notice, it doesn't look that much different than the original graph. You get a secondary hump over here that wasn't in the original. That was kind of hidden in the original. But you get the same feeling from the data you guys were talking about. It's slightly skewed. You've got a little bit more heaviness on this side than on that side. There's a spike over here, a secondary spike over here.
Sean, excuse me, and that is the average, right? Like that.
We're going to find the average in a second.
Okay.
We're going to find this average on that in a second. Because the next part of the discussion is actually to deal with this. And you can do this all day long. You can mess with those X scales. You can change X scale to just 5. Which will essentially double the number of bars that you see. Because now every bar is 5 wide instead of 10 wide. So now if you hit graph, it looks like that. So you see, there definitely is this recurring bar that's showing up down here. We're gonna address that in a second. But there comes a point when the number of bars gets to be too great. Like for example, if you make every bar too wide, okay, yay. But now it's like, okay, well, what shape is that? It's almost flat at this point. You see your mode. There's your mode at -20 and negative 25. But you know, you see what I'm getting at? So it becomes kind of a fine line as to how many buckets to have. So let's all settle. Do you guys have a favorite from the original? 7. You like 10? I think 10 is great because 10 allows us to actually kind of jump around the bars pretty easily. So we'll just change our scale to 10. I like that. I like that. And we're going to head. And if you're changing it, if you're changing window, you have to follow that with a graph push. You have to push graph, not zoom 9. Zoom 9, I always hit first when you first enter the data. If you start finagling with the setup of the screen, then you want to press graph, not zoom 9. Is that fair? Is that fair? Oh, yeah. You pretty much, for the 89, you pretty much always have to press window and finish, because zoom data doesn't seem to work on the 89 for whatever reason.
And no matter what I change the scale of the bars to, it stays the same.
Yeah, that's
Alright, though.
yeah, that's another one. Oh, that is yeah. So basically, what the scaling does on the 83s is when you make it 10, this is now 10 right there, negative 10, I guess, negative 20, negative 30, negative 40, negative 50, negative 60, and then you've got 10, 20, and 30. And I wish the TI actually gave you these numbers, but it doesn't. So you have to kind of just mark them on here. I'm going to put 30 out here. I'll put negative 60 here. Maybe put negative 10 for reference there. So I would call this data essentially symmetric. Essentially. I know it's not pretty. It's not perfect. George, I'm sorry. It's not perfect. And it will never be perfect. But it's not skewed to the point where I see an exponential shaped hump here or here. You've got most of your data kind of clustered in the middle and it kind of tails off. So the first question I have is, where's the average on this graph? Where's the average on this graph? Now remember, we calculated the average from the raw data, didn't we? So where is it? It's at negative 15 pounds. It's at negative 15 pounds. So if this guy's negative 10 right here,
1 over.
half over.
Half over.
Half over, right? Because if that's negative 10, that's negative 20. So your average is going to be right here. Call that X bar. There's your average, negative 15. Now remember, we lose the raw data by looking at it in a histogram form. We lose the raw data, but you guys could most likely figure out roughly where that average is with the balance point finger trick. But you don't have to, because the TI can calculate it for you, which is very, very nice, yeah. So, I want to discuss the average, negative 15, there it is, there's the balance point. I also want to discuss, not that I want to ignore the median in the mode, but I want to ignore the median in the mode right now. I mean, in general, I don't like ignoring them, but because I want to talk about Trevor's question, the standard deviation, I want to see what else it can show us besides just that it's 16 pounds. So what I want to do is, I want to explore that 16 pounds as it goes with this average. So what we're going to do is, let's go 16 pounds away from average on both sides. So at negative 15, if I go 16 pounds up from that, where am I going to be? Will that be a 1?
Oh, that way.
Okay. Oh, you guys are going this way.
Okay.
Well, we'll go both ways. I want to go both ways eventually. So if I start at, let me use different colors so it stands out on the screen. I'm going to ask for a projector. When I have an actual overhead projector, I can make it bigger on the board. I'm kind of stuck with the size of this now. So if I start at average, X bar, which is, I'll just put it down here, 15, and I go up to here, which would be at 1, negative 15, not 15, and if I go down 16 from negative 15, what would that get me down to? Negative 31, right? Right?
Yeah.
That's a range of values. That's a range of values. And that range of values, hey, let's just turn it off.
I know.
Silly. That range of values, which is now completely invisible because I used green. Let me use blue. That range of values between negative 31 and 1, those are in pounds. This is all pounds on this horizontal axis. That range of values is defined to be 1 standard deviation. Now, this is confusing, and I apologize for statisticians everywhere. Exactly, it's, I saw your bottom lip pop out there. Almost like a Freudian lip. Yes, it's confusing because that number is the standard deviation of the numbers. So on average, the average distance away from X bar. But when you add and subtract that number one time from average, you create a range of values. That range of values is called 1 standard deviation from average. This is just a definition. That's all this is. It doesn't mean anything. That's what it's defined to be. So 1 standard deviation from average. And sometimes the from average is left off. Sometimes that gets dropped. I'm going to keep saying it for a while because I want to keep driving home the point that it's tied to X bar. 1 standard deviation from average is defined to be the range of values that are exactly, or I guess not exactly, that are the standard deviation away from average up and down. So it's a range of values. For the weight loss data, that's negative 31 pounds to 1 pound. That tells us something, and I want to come back to what it tells us momentarily, not right now, not right now. That's just the definition. And there's lots of weights in there. Give me a weight that's in that interval.
Negative 30.
Negative 30.
Negative 10.
Negative 10.
0.
I was just thinking 0. Zero's in there, right? Zero's in there. 0. Negative 6. Lots of negative values. Lots of negative values. A couple positive ones, not very many. Not very many. You got 1/2, 3/4. Not very many. The vast majority are negative. The vast majority are negative. Cool so far? That's just defined to be one standard deviation from average. One standard deviation from average. Now, you can take as many standard deviations from average as you want. The most common is 2. This is the one you're going to see quite often in research journals and other places. 2 standard deviations from average would do the exact same thing, but instead of just going 16, 16, it would go 32, 32. It would stretch out even further. So each time you increase this by 1 unit, you bump out 16 more. So 2 standard deviations wouldn't just go to 1, it would go 16 more up to 17. And this one would go down negative 31, 16 more to 47, negative 47.
So then it'd be negative 47 to 17.
Yes, ma'am. And that would be 2 standard deviations from average. 2.
So the formula will be, okay.
You got it. 2 standard deviations from average. In quotes, means, and formula-wise, this is one of the few formulas I actually enjoy. Because it synopsizes, I don't know if that's a word, synopsize, it is, I don't know, Rachel's got it on camera, so I guess it's real, it's legit. So, 2 standard deviations start at the average, which is center, and add and subtract 2 of that magic standard deviation average distance. So in this case, it would be negative 15 plus or minus 32 pounds either way, plus or minus 2 pounds either way. So, and for the weight loss data, that would be, as I think it was Haley just said, negative 47 pounds up to 17 pounds.
So you could do like 10.
You could do 10 standard deviations, which you just go 160 pounds each direction, right?
Yeah.
Anybody ever heard of 6 sigma? Does that ring a bell for anybody? It's about a 15-year-old idea that's been, it was an efficiency kind of push, a cost-cutting efficiency push. And the idea of 6 sigma was to go out 6 standard deviations. So you would be going out 96 pounds in either direction from average. Now the kid, Jada's like, wait a minute, what the hell? You go out 96 pounds from average, you're talking about a person that's 850 pounds, or negative 230. And that becomes the reality, Haley. If you go too far out with standard deviations, you might run out of data. And that's what I'm going to come back to a Trev's question in just a moment here. What would 3 standard deviations be? Here's 1 and 2.
Times by 3.
We go down 16 more, right? So what would that be? 63 pounds, right? And up 16 more would bring you up to 33 pounds, right? I think you get the idea here. We'll draw it over here on the board. So negative 63 would actually be off the chart at that point, which is fine. And this would be 33 off the chart as well. Do you see how each succeeding interval picks up the previous interval and adds more to it? Hopefully that makes sense to you.
Right, because you don't want to go too far, because the biggest one is negative 58.
Exactly,
Right, so
exactly.
really
Now there are some data sets that escape even 3 standard deviations. There are some data sets that there will be data outside of even those standard deviations. What do we tend to call those data points? That's one way of quantifying the outliers. If they escape this average distance from average, they're too far up or too far down, and we call them outliers. It's one way to define it. But we're going to keep going back to that. I actually created an entire section called outliers. Your text didn't have one, and I thought it was important enough to talk about. So we'll get to that eventually, but I want to make sure we nail down this first. But back to Trevor's question. What else does this tell us? Well, there's a pretty important idea. Your book calls it the empirical rule, and I like that because I think almost every textbook in conversation in statistics calls it that. Depending on how many standard deviations you have, assuming your data is roughly bell-shaped, and this is arguably bell-shaped. It's not perfect, but it's arguably symmetric and unimodal. There's something called the empirical rule. Let's come on over here, and we're gonna mess with this throughout this course. So, when you have roughly bell, or sometimes, I think your book might call it mound-shaped data. And this is a big when, or if. This is a big condition. That is the condition placed on the data. It has to be that shape in order for this to work. So if you can say, yes, my data is roughly bell-shaped, roughly. We'll have all kinds of measures for this soon, I promise. So roughly bell-shaped data. So in case you're worrying about, like, well, how do I know if it's bell-shaped too much, not enough? We're getting there, When we talk about it enough, you start getting a feel for it. Then something called the empirical rule kicks in. Now there's a formula for it. I don't want to talk about the formula right now. I want to build the well, yeah, you'll see why in 3 or 4 weeks. I promise.
I just can't wait that long.
You can.
I'm just excited.
I know you're excited. I don't want to squash that excitement with a formula right now, though, Armand. That's okay. I hate to squash mathematics with formulas. I like formulas sometimes when they're timely. This is not timely.
A lot of times they just make me cry.
This one would make you cry. I think it would squash the excitement, though. So here's what I want you guys to take this in. We're going to check this data for it. These standard deviations, when you go out and create this certain range of values, and then you extend that certain range up. Let's go with color here. Okay. There's a big chunk of data that lives between those. So I said earlier, give me some numbers that are between -31 and 1. And you said, oh, well, 0's in there, and -15 is in there, and all kinds of... There's a set percentage-ish that actually lives between the -31 and the 1. And the empirical rule says about 68%, or about 2/3 of the data is within one, let's put that down here, is within one standard deviation. Roughly 2/3 of the data is going to live between the upper and lower elements of that one standard deviation. So what I want us to do right now is I want us to check that with our data. How much of our data is between -31 pounds and 1 pound? And this is where our sorted list is going to come in handy. Go back to your raw data, friends. Go back to your raw data. I'm going to go to the edit screen. I can do this one at home. There we go. All right, so -31 to 1. So there's -31. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I get 24 if I count -31 and 1. Go ahead, Jordan. Is that your question? So the question is, should I count -31 and 1? Is it parentheses? Is it brackets? This is not Math 111. I don't care. Count it if you want to. Don't count it if you don't want to count one. Don't count the other. Or this is all issues. So we're talking about issues here. And this is all rounded off anyway, right? So I'm going to count that as, what did I say, 24? So what percent of the data is that?
So together with 35.
It's
yeah.
24 divided by 35, right? There are 35 data points. So roughly 68%. Now, it's not perfect, but it's close. It's not perfect, but it's close. It's close. I mean, it's nice when data behaves like it's supposed to. Yay. It's always going to be an ish. It might be 72. It might be 62. But it's roughly 2/3-ish. And we're going to get a much better feel as the class goes on for ish. For that idea of ish. How big is too big? How small is too small?
And
24, did you just count all the numbers in the one standard?
Yes, ma'am. I started at negative 31, went to 1, and said how many were in there. Yeah, absolutely. That's all we did. That's all we did.
Real slow.
Cool. No, you're not. No, you're not at all. This is not this is not a trivial idea, my friend. It's not a trivial idea. So that's 1. Now the empirical rule actually has a whole lot of percentages for any number of standard deviations. So back to Haley's question, that great question about, can you go out 10? Sure. You can go out 9. You can go out 8. You can go out a half if you so chose. You can go out a half a standard deviation. You can say, well, if that's 1 standard deviation, then a half would be 8 pounds. So you can go up and down 8. So pretty much the empirical rule is going to give you a percentage for any number of standard deviations. The ones that are commonly used are 1, 2, and 3. And some of you may have heard this in psychology classes if you've taken psych classes before. So here's the biggie. This is the big one right here. 2 standard deviations is essentially the most popular for a host of reasons, as you'll see in this class and also in 244. You get about 95%, or about 19 out of 20 as a fraction. About 19 out of 20. I'll put a tilde there too, because it is approximate. About 95% is within 2 standard deviations.
If you only went out half of a standard deviation,
Yes, sir.
does it cut your percentage?
No, great question. Awesome question, David. David asked the question, if you only went out half a standard deviation, would that cut the percentage to 34? It's actually much higher than 34 because of the shape of a bell curve. It's not, if the bell curve were a rectangle and you chopped half off of either end, then yes, it would be exactly half. But there's more towards the average than what falls away from the average. So if you chop those outer parts off, you're not removing exactly half of what's there. You're removing less than half of what's there. Fantastic question. We'll revisit that one too as we go through the course. Does that make sense?
Yes.
Yeah, exactly. It's all about the shape. There's more in the middle than there are in the tails. So let's check our data. Do we have roughly 95%? I don't know. Let's go look. Back to our raw data. 2 standard deviations, as we calculated, was negative 47 to 17. So let's check our data points that are between those. So let's see. Edit. Okay, so starting with this one, right? So negative 38's in there. And I'm gonna, you know what we're gonna do? Let's do a little trick here. I'm gonna go up. If I go up, it'll put me at the bottom. So 21 is outside, isn't it? Is 16 in?
Yeah.
16's in.
So just subtract the top.
That's what I'm thinking. The top and the bottom are not in, so there are 33 that are. Does that make sense? You can do that. If you need to move around a data set, you can go up through L1 and it'll put you at the bottom, which is kind of slick. So 33 out of 35, that's pretty close, I think. I think that's pretty close to 95, huh?
94.
Yeah, there it is. Ish, 95%. Ish. I know this drives algebra students nuts. The hell, ish, it's not 95. I know, this is statistics, this is real data, it's noisy, it's messy, it's just what it is. But I stay close to 95. That's the important part. And the last one that's often used is 3. I know we didn't calculate it out. I mean, we drew it up here. It's from negative 63 to 33. But essentially, almost all of your data should be within 3 standard deviations, unless you have some goofy outliers that are going on. So essentially, roughly all the data, and I think the percentage, I want to go by memory here, don't trust this, so we'll come back to it later in the course. I think it's about 99.7% of the data. Is within 3 standard deviations. And you can see that all of our data is within 3. The negative 58 is bigger than negative 63, and our 21 is below 33. So 100% of our data is in there. As the data sets get larger, more and more of that cool fluctuation happens. Even a normal data set will have outliers. Every data set has a largest value, every data set has a smallest value. It's just that as they get too large and too small, we start questioning whether or not they're representing what's going on. This also tells you, friends, why, I'm going to put the graph back on.
So what's the 3? It's negative 63 and what?
To 33, I believe, 16 plus 17 is 33, yes ma'am.
So,
So 3 standard deviations would be x bar plus or minus 3 s's, which would be negative 63 to positive 33.
okay.
Which means we should have just about all of our data in there. And it is.
Right.
Because all the other 35, the other 33 that were in here are still in that one because it just got wider. And that extra one that was down here is in there, and the extra one that was up here is now in there too.
So would it just be 100%?
For us, yes. That's why I said roughly all the data should be in there, and ours ended up being in there.
Okay.
Now, I say roughly. If you've got, say, 10,000 data points, you may have 10 or 20 of them that aren't in there. But that's what it says. It says about 99.7%. So you should have 0.3% that, on average, are not in there.
Right.
And more on that when we get to larger data sets. I like the little small data sets first, at least with raw data. I mean, I can't have any guys 10,000 data sets in the exact number. No, that's squashing excitement right there is what that is. Fairish? Ish. Fair. More questions? Trevor, I'm answering your question more, I hope.
Yeah, it's
We're getting some real good ideas about what's going on here.